Hello. In this video I'm going to go over the first problem from the first problem set of David Tong's lecture notes. So what we have is we have a string that has fixed endpoints, a distance a apart, and it can wiggle. And we want to build a Lagrangian for it. So how do we do that? Well, if we take our string and we look at one kind of infinitesimal element of it, and we say it has a mass dm, and we call its displacement from its equilibrium point y, then the kinetic energy of that little piece of string will just be 1/2 mv squared, which is 1/2 dm y dot squared. And if we assume that the string has a mass per unit length sigma, then we can write our dm as sigma dx, and our total kinetic energy will just be the integral over the entire string of each of these infinitesimal kinetic energy terms. So we'll get this. So now the potential energy of the string. So we assume that the potential energy so this T is a proportionality constant, and it's just proportional to the total displacement of the string from equilibrium. So at equilibrium, if the string isn't wiggling, it will just have a length of a. It'll just go straight from here to here. But if it's wiggling, then that means it has to stretch to wiggle. And we'll just call that L for now. But L is basically, it's the length of this curve. And if we remember from basic calculus, we can find the length of a curve by doing this integral. Integral from over the string, from 0 to a, square root of 1 plus y prime squared. So y prime is dy dx. So our expression for the potential becomes this. And furthermore, if we assume that the displacements are small, so that this y prime term is small, then we can Taylor expand the square root to 1 plus 1/2 y prime squared. And so we'll have these two terms we have to integrate. But this first term is just the integral of 1 from 0 to a. So that's just going to give us a. And then this term's still here. But we have a minus a, so these two terms cancel. And we're just left with this, which is the expression he has. So yeah, so that's how he gets that Lagrangian for the string. So now that we have our Lagrangian, let's assume that we can write our y as a Fourier series, and the time dependence of y is going to go into the Fourier coefficients, these qn's. So we make this assumption. So we're going to need y dot and y prime here. So we need to calculate those. So doing y dot is very easy. We just take the time derivative of qn. It's the same thing, just with a dot. So when we're then we need y prime squared. So to do that, we have to make sure, so it's not just sum from n equals 1 to infinity of sine squared n pi x over a times qn squared. Y prime is equal to a sum here. So y dot is equal to this sum here. So when we do y dot squared, we need to do this sum times another sum. So we need another summing index. So choose m here, so y dot squared will be this. And y prime, the derivative with respect to x is, so we'll just get, from the chain rule, we get an n pi over a, and then the sine will become a cosine. So we get this. And then once again, when we square it, we need to have two sums. So it becomes this. So now that we have these two things, let's plug those in to our Lagrangian. So let's just worry about the kinetic energy term first. So kinetic energy term is this integral. So we need to plug in y dot squared here. And if we do that, so we can move the sums out of the integral, and just everything that doesn't depend on x, we move outside the integral, except for this 2 over a, we move in. And the reason we do that is because we can identify this thing, these sines functions are orthogonal over this interval. So this whole term will just give us a delta and n. So here. And then we can sum over m, and that will make this m go to an n. And so we'll still have this sum over n, but now, so we'll get a sigma over 2 qn dot squared. And then for the potential term, it works out very similarly. Pull everything that doesn't depend on x out, and we'll have this integral, which again, these are orthogonal, so we just get a delta in n. So we just change every m to an n, and this sum goes away. So we're just left with sum from n equals 1 to infinity, and, well, this thing. So our Lagrangian becomes this. And so now we can just use our Euler-Lagrange equations, and those are easy to do. We can just do it by inspection. So dl dqn dot is just sigma qn dot, and then we do time derivative of that, so we get sigma qn double dot, and then minus the derivative of this, we'll just get a plus this, and then divided by sigma, we have our usual harmonic oscillator looking thing. And so this is, so there's an infinite number of generalized coordinates here, one for each n. And so we have an infinite number of harmonic oscillator equations here, with frequency given by the nth frequency given by this.